Hi everybody, here is our video key for the in-class E2 practice activity. For the first problem, what I would do is immediately identify any beta protons that I have. I know I've got an alpha position here, beta position here, and beta position here. So if I think about the beta protons, I do have a beta proton coming off this left carbon, so I could identify that. And then I've got 3 beta protons over on the right as well. So I'm going to erase these alphas and these betas. All right, if we focus in on this beta proton, it must be a wedge because isopropyl group behind it is shown as a dash. So make sure when you do show this that you clearly show this as a wedge, not a straight line, and definitely not a dash. All right, so now if we look at this beta proton on the left, one thing that I'd notice is it's not anti to the chlorine right there. And what I mean by that is let's try to draw the Newman projection. If I were to draw the Newman projection looking down this bond right here, it would look like this, and I'll do that right below. I would have a methyl group sticking straight up, so I'll just say CH3. I'd have 2 legs sticking down like this. I would have the chlorine on the left, and I would have a hydrogen on the right. That's an assumed hydrogen coming off the front carbon, right? Off the back carbon, I'd have 3 prongs. Over here, I'd have the IPR, that's that group right here. And then on the left, I would have my hydrogen, and underneath, I would have my phenyl group like that. So as you can see, the chlorine and the chlorine and the back hydrogen are not anti to one another. So what I need to do is I need to move this beta proton, meaning this proton right here, in a position so that it's anti to our leaving group. So I'm going to twist it like this, which means that this isopropyl group will go over here, and then the phenyl group will go over here. So let's go ahead and do that Newman projection twist. The front carbon is going to remain exactly the same, so we'll leave that as is. Our phenyl group is going to move up to this corner, our hydrogen will be over here, and our isopropyl group will be down here. So now our chlorine and our hydrogen are anti to one another. So we can go ahead and we can say, all right, if we try to redraw this Newman projection as a bond line structure, we would still have the methyl group in the front, we'd still have our chlorine right here, we'd still have that hydrogen as a dash. But now if we think about what's coming off up here, the hydrogen would be a dash, and the phenyl group up here would now be a wedge, and then the isopropyl group would be like this. Really, if you go back to this original structure, this is the exact same thing as twisting this around, and so we're kind of just rotating everything around a little bit. All right, so now we can go ahead and we can try to do the E2 reaction on this. So if we go ahead and treat this with sodium ethoxide, the ethoxide is a very strong small base, and we know we've got this situated so that this particular beta proton is anticoplanar. So we can go ahead and we can say, all right, it's going to grab that proton, clamp down, and kick off our leaving group all in one step. All right, so let's see what happens to that interior double bond. We know we're going to end up with a double bond. On one side, we're going to have a methyl group, and we're going to have the leftover hydrogen, meaning it's these 2 things that are left over on that left carbon. They're still going to be coming off of that double bond in the end. All right, so now the question is, we've got 2 groups coming off this side. Which group is going to go where? Well, we know the leftover groups that we have on that side are the phenyl group and isopropyl group. So the question is, will the phenyl group be on the same side as the methyl group or as the same side as the hydrogen? What I like to do is go back to my Newman projection with things anticoplanar and then circle these groups. So these groups that I'm kind of highlighting in fluorescent green, they are going to be cis to one another. So you can see right here, the phenyl group and methyl group must be on the same side. So over here, that means that the phenyl group must be on the same side as this methyl group, right? And then on the bottom, down here, we know that the isopropyl group must be on that side. And if we want to draw this using our complete bond line structure, we can show it this way, and then we can alternatively not use that CH3 label. So the unique thing with this is when we look at this product, this is our Z isomer. It is impossible to get the E isomer with the double bond in that same position because you will never have a configuration that allows that beta proton to be anticoplanar while giving you the E isomer. So this would be the correct product for this reaction. All right. However, there's actually additional products. So let's go ahead and consider the additional products. The additional product that we could get for this reaction would be using the other beta protons that we had. So let's go ahead and draw this out again. We know we've got this isopropyl group hanging off in the original structure, got the chlorine off of a wedge, and then we said we have additional beta protons coming off this position. So I'm just going to really emphasize them by drawing them in red. So in this one, we've got ethoxide, the negative charge. Our base can grab any one of these because one of them will always be anticoplanar, and clamp down and kick off our leaving group. All right, in this particular situation, we don't need to worry about E or Z isomerism because our resulting double bond can't be identified as E or Z. What I mean by that is if we try to identify this double bond as E or Z, it's impossible. So for this particular problem, we would get this product down here, and we would get this product up here. So we would get both of these potential products out of this E2 reaction. Now the question is, which one is major and which one is minor? Well, if we look at ethoxide, that's the base that we're using right here. This is relatively small. Same thing down here, so I'll just label this small. We know that small bases prefer the Zaitsev or more substituted alkene. So in this case, the Zaitsev product would be the more substituted alkene, and this will be our major product. Down here, this would be our minor product, also known as our Hoffman product for this particular situation. All right, so that's the first problem. Let's take a look at the second problem now. So in the second problem, I would do the same thing. I would say, all right, this is my alpha position, this is my beta, and this is my beta over here. If we think about the beta protons, we've got a beta proton coming off right here that's assumed, and it must be a dash. And then on the other side, I have two beta protons. I've got one that must be a wedge, and then one that must be a dash. If we think about our leaving group, it's a wedge, which means in order for the beta protons to be anticoplanar, they must be dashes. So it's only the highlighted beta protons that would work. This beta proton right here is not anticoplanar, so we couldn't use that for our E2 reaction. All right. It's also important to remember that with chair structures, this bromine right here must be in the axial configuration in order to do E2 chemistry. That's the only position that allows both of these beta protons to be anticoplanar. If this top bromine right here were equatorial, neither of those protons would be in an anticoplanar configuration. All right, but in this situation, we actually don't even need to use the chair flip versions at all. So let's just go ahead and say, all right, what happens if we treat ethoxide with this? Well, we could get one where we go after this beta proton, kick off our leaving group. And if we do that, we would get this structure here with the double bond. And then this methyl group that was coming off right here, it was a wedge, but down here, it won't be a wedge anymore because it's coming off of a trigonal planar carbon. So I'm just going to have that shown as a straight line. So that's one option. Another option, if we think about ethoxide, would be to go after the other beta proton that's anticoplanar. So we could go after this one, clamp down, and kick off our leaving group, and get the double bond in the other position. So if we get our double bond here, the methyl group in this case would remain a wedge. So in this problem, we're going to get two different products. Whoops. We get this product right here and this product right here. So it's interesting. We get two different products. Now the question is which one's major and which one's minor. Again, ethoxide is a small base, which means it's going to favor the more substituted alkene, which the first one we gave would be our major product because it's a tri-substituted alkene. Or on the bottom, this would be our Hofmann product or our minor product. So we can quickly go through these problems without necessarily having to work with a chair structure. All right, next one. If we look at the next one, we want to do the same thing. We'd say we've got an alpha proton here, got beta, and then beta. Now we need to look for beta protons. Okay, so off of those beta carbons, we've got a beta proton right here. That must be a wedge because the isopropyl group's a dash. And then for the other beta proton, it must be a dash because the isopropyl group is a wedge. Given the fact that our bromine right here is a wedge, our beta proton must be a dash in order for it to be anticoplanar. So this one that I've highlighted would work. This one can't be anticoplanar, so this won't work for an E2 reaction. All right, so now if we go after this with sodium ethoxide, we really only have one beta proton we can pick. It would have to be this beta proton that I highlighted, clamp down, and then kick off our bromine. So we could go ahead and say the double bond would definitely be here. The isopropyl group wouldn't be a wedge anymore because it's a trigonal planar carbon that we've created. However, the isopropyl group over here would look like this. So for this problem, we wouldn't even get a minor product. We would exclusively get this product as our only product. So this would be an example of a stereo-specific reaction. All right, the next one. If we look at this, we've got an alpha proton, beta, and then last but not least, beta up here. If we think about this beta proton and this beta proton, they're really equivalent because they're symmetric. They're mirror images of one another. So I'm just going to focus on one of these because it doesn't matter which one we select. All right, so let's draw in our beta protons. We've got two right here. And then I've got three coming off of that methyl group right there. All right, now I'm sure you're wondering, we've been focusing a lot on finding a beta proton where, for example, this is a dash and this is a wedge. But in this situation, it doesn't really matter because this carbon right here isn't even a stereocenter. So we can't really determine whether or not it is a dash or a wedge because ultimately it doesn't matter. All right, so now when we work on this one, we can say we've got different types of beta protons we can select. In the first one, I could go after this beta proton, clamp down, and kick off our leaving group. That would give me a product with the double bond right here, and then the remaining methyl group will be hanging off. Alternatively, what I could do is go after the beta protons coming off of the methyl group. So I could say, well, what if I went after one of these, kicked off the leaving group in this manner? Well, if I did that, then I would get a double bond in that position. Again, we would get a mixture of two products. Now again, we would have to analyze our base to really determine whether or not we would get our less substituted or a more substituted alkene. Because this is a small base, it's going to favor the formation of our more substituted alkene. So this would be our major product, and this would be our minor product. Again, the major product in this case would be our Zaitsev product, and the minor product would be our Hofmann product. All right. Let's try the next one. Again, if we look for beta protons, we've got beta carbons right here and here. And we've got beta protons coming off the right carbon, and then off the left carbon, we've got two beta protons. However, when we're looking for the beta proton that's anticoplanar, the only one that would work would be the one that is anti to our leaving group. So both of these highlighted protons would be acceptable. All right. So now let's take a look at what happens when we work with a strong base like tert butoxide. Well, we could go after this proton on the left, clamp down, and give us this product, where we've got the double bond right here. The methyl group again wouldn't be a wedge because it's trigonal planar. It would just be a straight line. Or we could go after the other position. So we could say, let's go after this beta proton, clamp down, and kick off our leaving group. In which case the double bond would be in a different position, be right here. All right, so now we know we're getting a mixture of products, but in this case we've got a bulky base. We know that bulky bases favor the less substituted alkene, which would be this one down here. So this would be our major product, even though it's a less stable alkene. That's the result of using a strong bulky base. The bulky base in this situation has a really hard time going after this proton because it's in a really crowded nook within that cyclohexane. So instead, it would prefer to go after the beta proton on the other side that's more sterically accessible. All right, so that would be major. The top one would be minor. And this reaction, because it's giving a mixture of constitutional isomers, would be regioselective. All right, let's try this next one. In this next one, we've got two beta positions. Again, the beta carbon on the right has a beta proton. The one on the left also has a beta proton set. However, the beta protons must be anti to our leaving group. This one right here can't be anti ever because it's always going to be cis or synd to our leaving group, so it won't work in this situation. So really we only have one beta proton we can select. So in this problem, the only beta proton we can go after would be this one. Kick off our leaving group, get a double bond right there, and then our methyl group right here would remain a dash. So this would only give us one product, therefore this reaction would be stereo specific. All right, I think that was the end of the worksheet. I've got the key also posted in OneNote that's a little bit neater and more organized than a lot of this that I worked through pretty quickly. But if you have any questions, you're more than welcome to email me. All right, good luck studying.